Welcome to the Rich Report, a podcast with news and information on high-performance computing. Today, my guest is from a new company, A3 Cube, and they are the makers of something called RONNIEE Express. And today we have the CTO of the company, Emilio Billi. Emilio, welcome to the show today.
Thank you.
Well, thanks for coming on, Emilio. You know what I thought we'd do? Why don't we just go into your slides? You can tell us about the company, your new technology, and then we'll do a question and answer at the end.
Okay, perfect. So very quickly, it's a pleasure to introduce my company. So the A3 Cube was founded in May 2012, but is the result of more than 5 years of stealth mode operation, where we develop all the algorithms, the software, the firmware, and the hardware behind RONNIEE Express technology. So our company is today basically made by engineers. So we are all engineers. We are under 25 employees. And all our team, because we are a team, is coming from Cisco, Ericsson, and other big companies with expertise in networking technologies and storage. So we developed this technology in the latest 5 years, and we filed 3 patents. They are now patent pending. And this goal of our technology was to remove the bottleneck between the CPU and the computation, and introduce a new concept of architecture to create a storage and analytics machine. So if you go to the slide 3, you find the point that aims our intention. So we realize that because we're coming from the high-performance computing, that now the most important shifting in the paradigm is that high-performance computing is moving from computation to high-performance data. So data now are becoming more important than numbers. Most of the supercomputing operation, especially in the future, will be done into the data analysis, not anymore in the computation. So if you think that the power of the CPU today are enormous, the real bottleneck is the time that the CPU waits the data from the storage. So in most of the cases, you spend more time in waiting data than in the computation itself. And looking into the emerging technology to solve this problem, we find that the solid-state hard drive are really good to solve this problem locally. But when you want to think about a very parallel machine, massively parallel machine, and that would like to address the massively parallel scalability of the data analytics software, there is a problem in the communication between the local and remote node. And in most of the cases, you lose the performance that the solid-state hard drive gives to you. So the idea was that behind this concept, the storage doesn't scale linearly. And you say, why? This is you just add some hard drive to the existing node and you scale in capacity. Yes, but in high-performance computing stuff, the capacity is just one of the dimensions of the storage performance. Most important are bandwidth, IOPS, and latency in access to the data. If you buy an SSD, you don't buy an SSD because of capacity, because it's too expensive. You buy for the IOPS, you buy for the bandwidth that you can achieve access into the data, or for the latency, low latency in access to the data, not for the capacity. So when you scale, you want to maintain this linear scalability in performance to extol all the potential that the new technology can give to you. So this was the starting point. With this concept in mind, we start to investigate where is the bottleneck. And we realize that the bottleneck is into the communication method using where you want to connect together multiple nodes and create a really computation and storage merger machine that grow and scale linearly in a massively parallel way. Now, all the interconnection of the storage and the computation are done using Ethernet, emerging new parallel computer using Ethernet, RDMA Ethernet, or InfiniBand. But from our point of view, from the storage, extolling the power of the SSD, these interconnections are not good. They are good for clustering, they are good for message passing interface, RDMA is exceptionally good, but we want to add something else. For that reason, we create RONNIE Express. If you go to the slide 5, I would like to introduce the RONNIE Express itself. RONNIE Express is an extension of the PC Express that is used as a data plane. So we don't want to compete with Ethernet or InfiniBand. So we don't want to replace the Ethernet inside the data center or inside the cluster architecture. We don't want to compete with RDMA of InfiniBand. We want to extend something that you already have local, that is your CPU to I/O communication mechanism between the CPU and the I/Os, happens using PC Express interface with memory mapping feature. So this is really extremely low latency interface. It is the lowest latency interface that easily accessed inside the member. You imagine that also InfiniBand card plug into a PC Express slot. So the latency of InfiniBand is in any case higher than the native PC Express because you have the PC Express plus something else. So the PC Express itself is the extremely low latency interface that you can have in your member. We would like to take this approach, the memory mapping that happens locally to address the solid-state hard drive and all the high-performance I/O, and extend this outside of the box without changing the communication paradigm. So the difference between us and other companies that use PC Express to do fabric is that we don't want to encapsulate Ethernet on top of PC Express. We want to use PC Express with its memory mapping capabilities outside the single box, creating what we call a distributed shared memory mapping network across multiple nodes. In doing that, of course, we immediately find two limitations, enormous limitation in PC Express. The first one was that PC Express was designed to be local. So it's very good for memory mapping locally, but if you want to scale out of the box in a massively way, you find that PC Express completely lacks of congestion management, traffic congestion management, and flow control. So your network became really, really complex to manage. And the second point was related to the first one, is the topology. PC Express supports only 3 topologies. And also with the new non-transparent bridging, you can address simple topology, like a star, but very few nodes. So this is a big limitation if you want to think about high, massively parallel supercomputer concept. And for that reason, if you go to the slide 6, this PC Express architecture, without changing the communication paradigm, adding some special feature that permit to us to create something unique. The first idea was to introduce a multidimensional topology on top of our NIC. And this multidimensional topology permits to us to address a 3D torus topology like Cray supercomputer or Blue Gene or Fujitsu, adding also all the quality of service and the flow control, the virtual channels and so on. The routing algorithms are driven through reconfigurable routing tables. We use the wormhole with deadlock-free algorithm for point-to-point communication and routing. So it became a true supercomputer-style network for commodity hardware. The second point was to add to the end-to-end traffic management. So it means that you can packet arrive at destination independently from the path that it takes. And also a link layer flow control with hardware-based high availability that permit to us to modify the routing table in case of failure of one of the links and creating very high availability system. All that feature can be managed by software and hardware itself. So most of the features are automatically driven by the hardware, but you can also have a software control that permits to monitorize all your network in real time. And you can also modify in real time some parameters at very, very, very low level. So all this stuff permits to create a new kind of data plane external to your box that use the same paradigm of communication of the PCI Express inside the box. So if you go to the slide 7, very, very in a simple way, I made a picture, describe visually the mechanism, how it works. So you have multiple servers, in that case 6. Each server is connected to the fabric through its PCI Express interface and the non-transparent bridging interface to isolate the local memory from the remote one. This global memory creates what I call global shared memory container. Is a logical 64-bit address space. And what really makes RONNIE Express unique is that this shared memory facilities is done to create a high-level communication abstraction that permits to use the load and store operation of the CPU locally and remotely in the same way. So if I want with the local server to communicate with the remote one, I just read and write from the address of inside the memory that correspond to the remote server. And through the lookup table and some complex mechanism, the messages arrive to the memory. That's it. It's extraordinary low latency because you doesn't involve the kernel of the operating system. You completely offload the operating system from the communication operation. The synchronization of the memory is conducted at hardware level. And this is what I call in-memory network. So I put the network into the memory, extolling the power of the really low latency mechanism of reading and write into the memory and the low latency in the PCI Express to carry messages without nothing else more. So if you go to the slide 8, there are some pictures of our product, how our product appear. So you see three different shapes, same technology, 3 different shapes, and now I'll explain why. The first one was RONNIE 2, that was our first product designed to support 2D torus topologies and point-to-point communication, of course. And was designed for small system and was also our proof of concept. We start to make benchmark, optimizing and so on, and now it's fully debugged and it's ready to be used. So we decide to put as an entry-level product for us. Then we've developed what we call RONNIE Rio. That is our cutting-edge product. So it's a compact PCI Express, so it's really, really small, with the NIC inside and 6 connectors to create the 3D torus topology. This is the first 3D torus topology in outside PCI Express form factor. So it can fit in any kind of server, also very dense one. So the idea to use the 3D torus came to me because I'm coming from the supercomputing world. And the latency that we reach in our communication, that is in the order of 700 nanoseconds in point-to-point communication for 4 bytes of packets, is so low that also if we add multiple hops between the sender and the destination, the latency, the total latency is in any case very, very low. And in that way, we can completely avoid the use of external switches when you want to scale. So the network scale linearly without equipment. This means low power consumption. This means less space and also less price. At the end of the story, we add also RONNIE Free. This is a compromise because some of our customers asked to us to create something that was more easy to deploy than a 3D torus, just because they are confident with some legacy session system. So we create this RONNIE 3 switch that really embedded the 3D torus inside. But of course, you can have the illusion to cabling a standard switch architecture. So it's easy to manage for people that are more confident with what already they know. So this was our hardware ecosystem, and the reason for that our ecosystem is clear, and the scope was to create something that can scale in storage performance exactly how in the past cluster permitted to the computation to scale in terms of flops, floating point operation. To do that, we create also a completely software suite that we call BOS. BOS stands for Build Your Own Storage, but really is a massively parallel operating system based on Linux. So it's a Linux distribution, plug and play, that incorporates all the features that permit to us to extol all this capability without no configuration very easy in the way. This operating system permit also to create is completely memory driven that we call reflective memory distribution that permit to have a copy locally all the information related on metadata. So we avoid the use of a centralized metadata server. So the access to the node became extremely fast. And also the scalability became without a single point of failure. So we don't have to take care about the metadata desynchronization. That's a really important factors, because each node is completely autonomous, like in a distributed RAID multidimensional architecture. So this is more clear if you go to the slide 10. The slide 10 is exactly the architecture that we have in mind when we designed RONNIE Express data plane. So a massively parallel supercomputer created with the standard off-the-shelf hardware. So if you go in the corner, in the right corner, you have the idea of how this storage entity, so this server can be done. Very simple. Simple is absolutely better than complex. So we have just one CPU, some solid-state drive inside, maybe 8, not more, connected to the CPU using the PC Express SATA controller, for example. One or two interface, like 10 gigabit Ethernet InfiniBand for the connectivity to the rest of the world, to the rest of the data center, to other supercomputers. And the PC Express slot where we plug RONNIE Express. In that way, the focus is not the disk itself in our storage architecture, but it became the compute host, the microserver that we call the storage entity. Then we combine multiple of these storage in the way that you see in the big picture, and thanks to the RONNIE Express data plane, we connect all these servers together. The result, combined with BOS, is that all the pool of the solid-state hard drive that you have locally are merged into a single giant disk that has the capacity of the sum of each single hard drive into the storage entity. Our abstraction layer is a virtual layer that is provided by BOS, permitted to access concurrently to this unified storage. And all the synchronization operation and all the operation of the related to the storage, to the disk synchronization, to the file system synchronization, happens through the RONNIE Express that extend the same concept of communication from local to the remote one with a latency that is in any case under or at least closer to between 1 and 2 microseconds, also if you scale to a very large number of nodes. In that way, there is no any more latency in access locally or remotely. And since that we don't have the metadata centralized, but we have this in-memory reflective mechanism that permits the distribution of the metadata locally, we really can grow linearly. So this architectural approach is faster and achieved through linear scalability for distributed deployment of storage brick, just because each node is really independent and its communication algorithm is completely hardware driven, offloading in most of the cases, the CPU and the data center network for the operation related to the file system that are very intensive, especially when you grow to massively parallel scenarios, so thousands and thousands of nodes. The idea is now realized in a way that you can scale truly into the IOPS, in bandwidth, and in capacity. And the beautiful thing is that your data center network is connected to this new kind of storage using the standard interface that you already have. Because you can plug a 10 gigabit Ethernet as a user interface, InfiniBand if you use InfiniBand or whatever, and each server can provide a concurrent access to the same pool of disk. So you adding storage entity, you add also I/O interface to the external world. You have the concept behind the machine. So the architectural shift. So at the end of this design, there is a completely new view how the storage and the analytics machine can be done or should be done. So you have a complete separation between the data plane that provide all the operation for the aggregation and the synchronization and the communication between the nodes. And then you have the user fabric that you use for exchange data, for communication between two different machines or two different supercomputers or two different clusters. And all the operations behind the scene are completely transparent to the user. So you don't have to learn something new. You don't have to learn a new fabric that must be merged with the existing Ethernet. The data plane that we create is completely behind the scene. It's like a real supercomputer, where inside the supercomputer you have your ultra-fast network that provides the synchronization, the barrier, the process organization, and so on. And then you have your user fabric that is used to communicate with the supercomputer. The data plane is transparent to you. You don't have to care about how to integrate this network with the existing one. The same concept applied to a storage with the intent to create something that really fits with the exigencies of the new analytics massively parallel software like Hadoop, Implant, or Storm, and whatever. Additionally, this architecture is also very, very inexpensive because it can be deployed using low-cost commodity hardware. And also when you scale to 1,000 and 1,000 nodes, you don't have to buy external networking equipment like very expensive high-speed switches because the 3D Torus provide this feature internally at the NIC. So you can really scale linearly also price in terms of price. And one of the most important things that I forget to mention that we can use this architecture also with the standard application to create a computing and merger storage machine that is the architecture required by Hadoop, because we create a TCP/IP socket that works completely in memory, bypassing the operating system and the kernel, and works thanks to the lookup table and the memory mapping using the same mechanism that use RONNIE. In that way, also our TCP/IP socket has a latency of the order of 1 microsecond. In real benchmark, NetPerf and NetPipe demonstrate that the latency is in the order of 1 microsecond without using RDNA feature. So your application like Hadoop can run on top of this architecture without any kind of code modification. And this is really important because if you want to extol the power of InfiniBand, you have to use RDNA. But you use RDNA and you have a socket-based application, you have to port your application into InfiniBand. And this requires time and money. And not if you have not the access to the source code or the capability to modify the source code, you can do. So this permits to use your standard socket-based application, so TCP/IP application, on top of RONNIE Express data plane, achieving 1 microsecond of communication latency on the order of 1 microsecond latency, just in a plug-and-play way, without modifying nothing. So you can see that the application in high-performance analytics are enormous. This became a really supercomputer for analytics machine, dedicated to an analytics world, where the computation can grow linearly like in a cluster system, but also the storage access, so the performances of the access to the data grow exactly linearly how the performance grow in the same way. So if you go to the slide 12, you have some potential application where you can really use this architecture. The big data is perfect. The biotech and genomic research require big data sets fit perfectly, but also high performance computing and computing fluid dynamics, because most of the time you have to compute a very large data set of data. Imagine computation fluid dynamics when you have the mesh preparation and the mesh is really, really big, and you have to carry this data from the storage to the computing to make the operation, and the bottleneck became the communication between your storage and your computing. So it's, and other than that, computation fluid dynamics or lattice QCD take advantage from the 3D torus topology, because you can map the problem, especially in lattice QCD, on top of the 3D torus. And these 3D torus have extremely low latency. So it's something that hardware that is commodity. Then you can also embed this architecture into into building blocks for embedding system. Imagine parallel storage, proprietary parallel storage, redundant server thanks to the reflective memory. You can create a copy of the same information in two different memory, and also the copy of the disk. So if one server fails, you have a real-time backup of your information also in memory. You can use in embedding computing. Imagine medical devices like tomography. They have to exchange a huge amount of data between the equipment to the storage for the post-processing, and another application. So, but this is born to create a massively parallel architecture in storage world, changing the paradigm how to create the storage. The storage became the new supercomputer in a short word. And going to the slide 13, you can see some benchmark of the operation of our TCP/IP socket in memory. We have also a method passing interface completely in memory. But, okay, in that case, it's a TCP/IP benchmark. So you see the sock perf, the net perf, and net pipe that measure the number of messages that you can exchange in terms of TCP/IP, the first UDP, the net perf, and also the latency. We compare the latency with the standard PCI Express approach that encapsulates the Ethernet on top. And we have also the socket performance of InfiniBand. So without RDNA, InfiniBand is low power in terms of socket, and the performance of RONNIE Express, that is an order of magnitude greater. In the slide 14, we have an example of how you can create an extremely high powerful architecture using just a few nodes. For example, RONNIE 2 is a 4 connector, so I say that it's for the 2D torus, but we support also other topology. So you plug our PCI Express RONNIE 2S, that is also really low cost effective. You can use its 4 connectors to connect directly all the other nodes up to 5. So you create a completely point-to-point fully connected architecture. Each of these servers has inside a CPU and a small set of disks, in that case just 8, and aggregation make, of course, 40 terabytes, 8 by 5. If you measure with the I/O zone, the IOPS that you can install using standard solid-state hard drive, SATA, not PCI Express, SATA solid-state hard drive, so also cheaper, you achieve 4.2 million of IOPS. This is not an optimized system. This is a cost-oriented system. And if you compare with some on-the-market system that has the same capacity from a proprietary company, you see that they use a standard data plane, so the IOPS doesn't scale. It cannot scale. You have 8 times the performance in terms of IOPS, same capacity, but 8 times of the performance, with a cost, the total cost, that is less than 1/3. So the most expensive stuff that there is inside are the solid-state hard drive. But you can choose any kind of solid-state drive. So you are not related only to a specific model of store or hard drive. You can use whatever you plug into a PCI Express through a controller or directly. In the slide 15, I have what I call a positive drawbacks. That is just a consequence of the 3D torus. So if you think to scale a massively way, so 10,000 or not, imagine to create a really massively parallel processor, you don't have external switches. So if you want to use another data plane instead of the RONNIE Express as a network inside to aggregate the disk and provide the computation synchronization and whatever, you have to buy also external switches that are really expensive. In that case, we completely avoid the use of external equipment, so you don't have at least the power consumption of the external equipment, but also the footprint that they take. So it became lower power, you save the footprint inside your data center, and it fits very well with the concept of the solid-state hard drive that aims to be faster, low power consumption, and also you save footprint compared to the magnetic drive. So this is just a drawback that comes for free from the 3D torus, but it's something that is really positive in any case. At the end of the story, so this is a new concept to create a massively parallel architecture that seems to come from the past. You remember the connection machine, for example, because we are really, really convinced that high-performance computing will move performance data. So data will become a part of our life in terms also of scientific research and supercomputing.
You know, I wanted to ask you about if I was going to build a cluster based on RONNIE, do I have the option of keeping my Ethernet interconnect and using RONNIE for the data plane, or how would that work?
Correctly, exactly. This is correct. It's exactly what you can do. So you use Ethernet for your external connectivity to connect to the user network, and you use RONNIE for the data plane, like in proprietary supercomputer stuff.
Sure. And then, do I have to change my programming model, Emilio? I mean, do I have to switch from MPI to OpenMP or something like that? Okay,
very good question. So we work to permit to you to use TCP/IP based application. We created the message passing interface, so the MPI, that run in memory, so you can use your MPI application on top of that. We are working to port the PGAS application and middleware, and we have also a set of API very easy to use if you want to create a native application. So if you are a supercomputer software engineer, you can extol the pure performance of the communication using the direct API. So in that case, you can create a cluster of pure GPU, because thanks to this memory mapping, you can extend the peer-to-peer capability of the PCI Express also outside the box. So you can create a cluster of accelerators, and of course you have to buy the driver and other stuff. So we have, for existing software, run transparently to our architecture, and if you want, you can also create your own next generation application thanks to API library.
Okay, so kind of a wrap up here, Emilio. We're reading a lot today about in-memory, right, analytics, and in this kind of implementation, a RONNIE cluster, is this similar? Is this delivering me a huge memory with low latency?
In that case, we use the memory as a network, so it's a complementary way to see the things. So instead to put just the computation in memory, we use also the memory for the communication. In that case, if you merge the two words, you can really create something that is disruptive. So memory for the computation and memory for the communication.
Very interesting. Well, Emilio, I want to thank you once again for coming on the show today.
Thank you to you for your time, and it was a really pleasure.
You bet. Okay, folks, that's it for the Rich Report. Stay tuned for more news and information on high-performance computing.